Today we will be talking about the mechanisms of strengthening in metals. My name is Josh Luckman, and joining me are Ruben Brown and Mavish Ganjor. There are three main methods to strengthening materials, with each of them having their own unique characteristics. These methods are strain hardening, solid solution strengthening, and grain size reduction. We will begin with Ruben speaking on grain size reduction.
Grain size reduction, in simple, is a method of strengthening materials by reducing their average crystallite size. By reducing these grain sizes, the amount of dislocations piled at a grain boundary reduces, resulting in an increase in yield strength. For now, we will go into a bit more detail. Grain size reduction relies on grain boundaries to provide constraint from dislocations moving and multiplying to the next grain. Polycrystalline metals are comprised of many individual grains and crystallites, as we can see in this image, also known as grain boundaries. These structures each have various grain sizes. At these grain boundaries, dislocations are constrained from entering the surrounding boundaries, leading to driving forces. Within each of these grain boundaries, dislocations occur when a material is under force. Dislocations will be given by the symbol of an upside down T. As we said before, at these grain boundaries, dislocations are restricted from entering the surrounding grain boundaries, leading to driving forces being created in an effort to push these dislocations to the nearby grain. As these grain boundaries expand and the grains get bigger, a bigger pileup of dislocations occurs in an effort to push these dislocations into the surrounding grains. For these large grains, lower forces are required to allow the dislocations to move to the next grain. In the next example, we're going to explore what happens with smaller grain sizes. By reducing the grain size, there are less dislocations within a grain boundary. Due to this, dislocation pileup will be minimized, leading to a smaller driving force. As there are less dislocations, a larger stress and force is required to push these dislocations to the surrounding grains. Because of this, the small grains require greater load than the large grains to move dislocations, meaning the smaller grains will have the higher yield strength. For polycrystalline metal, a decrease in grain size increases the strength of the metal. As strength is the capacity of an object or substance to withstand great force or pressure, the previous examples prove that the smaller grain sizes are going to be stronger. Now we're going to have a look at the Hall-Petch relationship. In order to find the potential strength of a material is capable of having after grain size reduction, a Hall-Petch relationship is used. The equation gives a theoretical yield strength of the material, and the equation is here on the screen, where K is the strength coefficient, which is a constant depending on the natural behaviour of the material, where the D is the grain size. As the grain size becomes smaller and smaller, the value of K will increase, and the rate of increase will depend on the material and the value of the K value. And sigma is the material's constant for the starting stress to form dislocation movement. In a real-life example, yield strength of nanostructured copper with a grain size reduced to approximately 20 nanometers can reach up to 800 to 900 MPa, a staggering 4.5 times its coarse grain copper at approximately 200 megapascals. However, after this stage, if the grain sizes are reduced any further past 20 nanometers, then the material begins a softening process, the opposite effect of what is being aimed for.
Now Mavish is going to introduce solid solution strengthening.
Solid solution strengthening involves the creation of alloys by dissolving one metal into another during the casting of an object. This can be done as the metals are still in liquid form, and as a result will allow other metals to diffuse into it. The creation of an alloy will involve a solvent, which would be the main metal, as well as a solute, which would account for all other elements. Each solvent has a solubility limit. This is the maximum amount of solute the solvent will be able to absorb. The black dots represent the solute being dissolved in the solvent. Excess solute will sink to the bottom, similar to salt in water. Thermal strengthening can also occur using this method, as increasing the temperature will increase the solubility limit, and adding solute will increase the strength of material by having excess solute when cooled into a solid. There are two main types of solid solution strengthening, which includes substitutional and interstitial. Substitutional strengthening involves atoms of a solute being bigger than that of a solvent. In a crystal lattice, this will cause irregularities. As a result, the material will require higher temperature or stress levels for dislocation to be altered again. This can be seen when making a bronze alloy with copper and tin, as tin atoms are bigger than copper and will alter the crystal lattice, increasing its rigidity. Due to this, bronze is often used for bearings due to its high strength as well as its high shock resistance. The drawing above depicts how a solid atom that is larger than the solvent atom can cause a dislocation. This will increase the lattice strength as the resistance for the atoms to move is greater. In an interstitial solution, the solid atoms are smaller and able to fit between the solvent atoms in a crystal lattice. This form of alloying will cause a dislocation in the lattice, increasing its rigidity and requiring a high temperature for it to move around. Steel is a very common interstitial alloy using iron and small amounts of carbon. The benefit of having this is that the carbon atoms will add strength as well as making it rust-proof, allowing it to be used to make cars and even safe for enough airplane parts. Smaller carbon atoms will tend to cause iron atoms to concentrate at the dislocation. This can be seen from the illustration where the white atoms converge at the dislocation around the small black atoms. This will reduce the mobility of the dislocation, allowing the material to withstand more force. As you can see from the trumpet over here, the vibrations when blowing into it would cause it to shatter if it was not an alloy. Due to it being made of brass, the structural rigidity is greater, and as a result of its dislocation, it is able to withstand more vibrations. Finally, we have Josh speaking on strain hardening.
Strain hardening, also known as cold working or work hardening, is a process where certain materials can be permanently deformed close to its failure point to increase its yield strength. This is a common procedure done to steel, aluminium, and copper. Cold working gets its name due to it being performed at very low temperatures below the metal's recrystallization point. There are many different ways to perform strain hardening under the four main methods: squeezing, bending, shearing, and drawing. Some of the minor methods can include cold forging, extrusion, and rolling. As the certain metals are deformed, it becomes harder to continue deforming them until it reaches its breaking point. This can be seen in steel wires or paper clips. When paper clips are bent, they become harder to bend in that same spot, but continuous bending will cause it to snap. When a material is permanently deformed, the dislocations inside the material move until they are stopped by something else in the crystalline lattice. One of the most effective dislocation stoppers is another dislocation. When dislocations run on different planes and intersect, they cannot pass through each other. The dislocations end up piling up on each other and make the metal much stronger. Strain hardening increases the yield strength and tensile strength of the material, but decreases the ductility. Strain hardening can be reduced by a high temperature heat treatment, but if a low temperature heat treatment is performed, it will cause it to become stronger. Although strain hardening may be beneficial to the material, as it does increase the strength of it, it also has its downsides. Strain hardening can make the material prone to corrosion due to the heightened dislocation concentration. Strain hardening can also cause unwanted residual stress. Both of these issues can be detrimental to the material's lifespan and cause it to fail.